Hello, my name is Edgar de Vries. I'm a hardware consultant with WellTyped. Today I want to talk a little bit about sources of quadratic core code size in GHC. And this is work that I did with my colleague Anders Leu on behalf of JustPay. Consider this module where we have a record with a bunch of fields. In addition to the record, we have some instances, show, eq, SOP generics to JSON, and we're using the record.preprocessor plugin to generate lenses for this record. Turns out, the size of the core generated for this module is quadratic in the number of record fields. And we will see in this presentation why that happens. By contrast, if we're using the large records library, the size of the record of the module will now be linear in the number of record fields. But we still get all the instances, including generics, albeit a different kind of generics, and the lenses. Does it matter? It does. If we have a record of 100 fields, the size of the AST in basic GHC goes up to nearly 500,000 nodes. That's terms, types, and coercions. Whereas for large records, the library, it stays down here at nearly 5,000. So that's nearly 2 orders of magnitude smaller. After the simplification, it's slightly less dramatic, but it's still 350,000 compared to maybe 30,000. So still an order of magnitude smaller when using the library. In terms of real resources, OS reported memory usage goes up to nearly 500 megabytes with core GHC, with basic GHC, whereas with large records, the library, it stays down here flat at nearly 100 megabytes, and this is normalized, by the way, to an empty module. And similarly, compilation time goes up to nearly 3 seconds with basic GHC and stays under 1 second with large records, so 3 times faster. Again, this is normalized to compilation of an empty module. There are two main sources for this quadratic code size. One is that we have no way of accessing or updating a record without mentioning every field, and we will see 2 examples of this. And then the more tricky one is that we have no way of introducing and controlling sharing at a type level. And we will see a few more examples of this because this is the more difficult one. So first of all, records. The moment that you define a record in GHC, you get quadratic code size right off the bat. Why? Well, GHC generates field accessors. Each of those field accessors has a pattern match on the record and extracts exactly one of the fields of the record. Since every field accessor needs to match and mention all the variables in the record, each field accessor is itself linear in the size of the record. Since we have one of these for every field in the record, that gives us quadratic code size immediately. Similarly, for the lenses generated by the record.preprocessor plugin, those lenses look like this. Like we have the accessor generated by GHC and we have a setter, which is just a field override. This looks fine, but after desugaring, it looks like this, right? We have 2 of these pattern matches now, and then for the setter, we also have a third of these blobs where we are constructing the original record, except that we're overriding 1 field in the record. Right? So clearly this is linear in the size of the record, and we're going to have one of these lenses for every field in the record, so again, quadratic code size. The second example in this category is type class dictionaries. So if we consider this class here, which is meant to capture the concept that some constraint C applies to every field in the record. In core, this looks just like the definition of a record, right? We're going to get a type class dictionary, which is going to have 100 fields, 1 for every superclass constraint, and accordingly, GHC generates 100 accessors, right? Each of those accessors does a pattern match. Those pattern matches are linear in the size of the record. We get 1 for every superclass constraint. So a class like this is quadratic in the number of superclass constraints. And if we have 1 for every field in the record, that means it's quadratic in the size of the record. Okay, let's move on now to the more subtle problem, which is types. Consider this function zip, which is going to zip 2 records together with given some function that we are going to apply pairwise to every field. Now clearly we're going to have to apply this function once for every field in the record, right? So clearly we're going to have 100 of these applications. That's expected. However, if we look at this in core, each of the applications of the app operator, the applicative app operator, has a type argument. That type argument tells us the types of the arguments that we get to apply. That argument is itself linear in the size of the record, right? First we have all the fields, then 1 less, then 1 less. And so this means that although we have 100 lines, each of those 100 lines is itself linear in the size of the record, and so this function all by itself is quadratic in size. As another example, consider this type of heterogeneous products, right? So this is coming from the SOP library. It's indexed by some functor and a bunch of types. So we can construct an NP, a heterogeneous product, from our record simply by just consing all the fields together, right? Easy enough. But although we have 100 applications of this cons operator, those cons operators have a type argument. That type argument tells us the type level list of the fields yet to come. And so in core, this looks like this, right? Where we have 100 applications. Each application tells us the tail of the list. The tail of the list is linear in the size of the record, just like before. So this is quadratic in the size of the record again. Now, the previous two examples were examples where we were writing the code. The next two examples are examples where GHC is writing the code. Consider this definition of singletons for lists, along with a class that says that we must be able to produce a singleton for a given type level list, right? Which has a standard two instances, one for nil and one for cons. This is fine by itself, but the moment that GHC needs to generate evidence for slist I for a concrete type level list, it's going to look something like this, right? If we need to produce a slist I instance for a list of 100 elements, we're going to have 100 of these scons applications. That scons application has a type parameter, right? The tail of the list. That tail of the list is itself linear again in the size of the record, and so quadratic code. As a final example, consider this this type definition for this definition of a type family which computes a constraint. This is coming from how the large records library deals with generics. It doesn't really matter what it does too much for the purposes of this talk, but the only thing that matters is that we are looking at every pairwise element of these lists and computing some kind of constraint applied to these elements. Right? So we have a constraint here and then whatever else. Now this is fine, but when GHC needs to produce evidence for a concrete type level list, it needs to produce evidence that looks like this. We're going to have 100 cons applications, right? This cons operator here. Each of those has a type argument. Again, it's the type of the evidence yet to come. That evidence is, the evidence for all other arguments, then for one fewer, and so again, that type argument is itself linear in the size of the record, the size of these type level lists here. And so quadratic code. So how does the large records library manage to avoid all this? Well, when you define a record like this, what gets spliced in is actually something like this, right? The record just becomes a vector of any. So GHC does not see at all that this is a record. We're basically giving up on type safety internally in the library. The user still works with the type safe interface, of course, but internally we have no type safety at all. So since this is a record, since it's a vector, we can just get an element from the vector or set an updated element from the vector easily. And that means that we can then define accessors which just use the vector get. And we can define lenses that just use the vector get and vector set. Of course, we still have 100 accessors, so we still have 100 lenses, like linear, but each of those accessors or each of those lenses is itself constant space, right? In fact, they're tiny. So this is not quadratic. We do not currently provide a pattern synonym for the record because the moment that you define a record pattern synonym, GHC produces field accessors for every field in your pattern synonym, and we're back to square one. GHC 9.2 has no field selectors, so that might hopefully make it possible to define a pattern synonym, but I haven't yet experimented with that. The other thing I want to show you is how we deal with the dictionaries. Remember, so not only do we have our own representation for records, we're also going to have our own representation for dictionaries for those records. Because I showed you before that defining a class that has n superclass constraints results in something that is quadratic in n. So how do we avoid this? Well, we're also going to have our own representation for the dictionary. And that representation looks like this here. It's the rep, R here is some sort of record, with dict C. What is rep? think of rep as a vector that contains an element for every field in the record wrapped in some sort of functor f. Right? And in this case, the functor that we're choosing is dict_c, meaning that rep of dict_c is a vector that has a dictionary for every field in the record. In other words, it's a type this dictionary, but we're using a vector rather than a record. We then have a single instance that produces one of these dictionaries, right? A single instance for this class. That instance has 100 superclass constraints, but that's okay. This will become a function that has 100 arguments, so linear, but there's no compounding factor, right? So it takes 100 arguments and then basically just sticks them all together in this vector here, and that's it, right? So it doesn't need to do very much more than that. And it's linear in size, not quadratic. Now, this thing is called rep because it's the generic representation of something, of a record, in large records generics. But notice here that this A is phantom, right? Meaning that we don't have any type level lists almost anywhere, because it's very difficult to work with type level lists in a way that doesn't result in quadratic code size. And the final thing I want to show you is this function normalize here. Now, normalization, again, is part of how large records does generics. That's a topic of a different talk. For the topic of this talk, only two things matter. We have some kind of constraint here, but the function is unsafe coerce, meaning the constraint is important for safety, but we're not actually using any evidence. So what is this constraint here? Well, it's actually just a wrapper around this interpret2 function that I showed you before, right? And I showed you this function because I said it was no good, right? If we have evidence for a particular concrete list, then that evidence will consist of 100 applications of this cons operator here, this comma operator, each of which has a type argument linear in size of the record. So this is no good. So how do we fix it? Well, we actually define a slightly stronger version of this. Rather than saying that these things must be coercible, we're going to say that they must be equal, right? This coercible here. We're going to make that stronger and say equality. What does it enable us to do? We can now define this like follows. We're always going to compute the trivial constraint. When we have two elements to compare, we check if they're equal, which using this potentially stuck type family, right, partial type family. If they're equal, we just continue with the rest of the list, eventually coming down to the trivial constraint. If they're not equal, this doesn't reduce at all, right? So that means that we get no evidence, which is what we want, and therefore the evidence that we generate is not quadratic. It's in fact constant, right? It's the trivial evidence. So to conclude, avoiding quadratic code size is difficult. It's often that I was working on this and I thought, surely this is going to be fine, and then I ran my benchmarks and oops, quadratic code. So it's not easy at all. Large records does it, but at the cost of internal type safety. We have also no support for unboxed fields. We could do it, but it would make a whole lot more things more complicated. Now, of course, it's a huge hack, right? It would be much nicer to do it in GHC itself, but I think that would not be easy at all. Especially the type level stuff is probably worth a PhD or two. That's all I wanted to talk about. If there are questions, I will be more than happy to answer them. Thank you very much.